Hello, everyone. Welcome back. So this time I'm not the last presentation before a meal, so I can take my time. Although we started 25 minutes late, it's fine. We're in Egypt, so this is Egyptian appropriate. Yes. So this presentation is also related to the work we talked about earlier today, but with a different approach. The goal was to work on a multi-waste upcycling for pavement. So the idea was to replace the raw material that we are mining for new construction as much as possible and utilize some of the waste that ends in landfills through some combination to upcycle them into a product that is of higher value. So that's the difference between upcycling and recycling, where recycling, you reuse the material as a lower quality. In our case here, we're trying to upcycle them as a higher quality product. This is, again, I'm not sharing with you the full study. So we took some incremental work. This work was part of the PhD work for Ahmed, who is now an engineer at California Department of Transportation. He defended this in 2022. Yes, 2022. We continued to do some work after that, applying life cycle assessment as well. And a lot of his work is already published. We have also Constantine help us with the fly ash component. So a quick background on this. We had a project since 2010. Actually, it's multiple projects that we kept adding objectives funded by the agency that takes care of all the power generating plants in the US that use coal for energy. And they typically end up with a lot of waste ash that they don't know what to do with it. So they came to us and thinking that pavement is a linear landfill. Obviously working with Constantine, he doesn't take orders. So we started thinking about how to make this even a higher quality product as much as possible. So in this work, since I've been working with fly ash in general for a long time as one of the waste and realizing types of fly ash that do not meet any industry, so ends up in landfills. We wanted to think about how are we going to deliver the fly ash into the system so that we can realize the benefits. And we realized also that there is another type of waste from some food products. I'm not disclosing what kind of food products at this presentation yet because we're working on a patent for it. So I'm sorry, but stays a mystery for a little longer. Through some chemical extraction, we managed to get some the bio oil of certain characteristics that have some rejuvenating effect on asphalt. So blending, the idea here was blending the waste ash and the oil extracted from the waste food together to create this additive that could replace part of the asphalt and in addition enhance its properties at the same time. But these rejuvenating effects of the oil allows us to use recycled asphalt as well and rejuvenate its properties. You know, asphalt as it ages becomes very stiff and brittle, so it's typically prone to cracking way more when it's recycled. Combining it with an anti-aging additive, which is the fly ash, and a rejuvenator, which is the food waste oil, and increasing the capacity for incorporating recycled asphalt, we could, you know, replace a large quantity of raw material that is being mined and reduce the cost significantly. So this is the whole story, very quick. And in order for us to visualize why this is important, this is a quick, you know, look at how the aggregate asphalt structure is used for carrying the load of traffic. The asphalt itself is not carrying, shouldn't be carrying any load. It's a binder to hold the aggregate structure together so it can carry the load. So in reality, what's carrying the load is the interlock and contact between the aggregate particles. And in order to keep them in place such that the stress is distributed over these thousands and thousands of contact points, we hold them together with the binder. And the binder itself is not just the asphalt also. Like we were talking earlier, it is the mastic. It's the blend of fines and asphalt. The weakest link in this structure is the binder. So we typically have failures starting with either overcompaction during construction, crushing the aggregate, but that can be mitigated through good quality control during construction, or failure within the mastic phase, which takes place either if you're using very soft materials, so it acts like a lubricant between these particles, let them slide against each other and deform, like in the form of rutting, for example, or if the asphalt itself is aged so that it would crack. So as I was saying, we're looking at 3 wastes to be incorporated, and we're trying to investigate the synergy between these wastes to see if this is really an approach that is worth further pursuing or not. These wastes are co-combustion byproducts, the ash, but not any ash. It's the off-spec ash, the ash that nobody wants to claim, and that ends up in landfills. The reclaimed asphalt pavement, these are the pavements that are removed, old pavements removed and dumped, and a food waste bio oil that is extracted in the lab. If you look at, for example, the fly ash, up until recently, we have been producing a lot of ash, but using almost 40%. Heating sources of energy like natural gas and so on. So the reliance on ash has been declining over the last few years, and utilization as a percent of ash has increased, and now we're at 60%. All the unused ash from way before 2000, so that all the stuff that is above the red line has been accumulating landfills for years. And we're still contributing to this landfill because, again, these are called off-spec ash. They vary in their properties depending on the source, depending on the power plant itself and how it was burning and how it was treated, the coal. But it's an abundant source of this kind of approach to mine as much as you possibly can and reduce, the footprint of these landfills. RAP, as the name indicates, is reclaimed asphalt pavements. So these are pavements that were removed, and we're trying to incorporate them back into newer pavements. However, their properties, the asphalt specifically inside the RAP, has been exposed to significant amount of oxidation that leads to significant change in its properties. Yet the aggregate inside that RAP is of good quality. So why use it in landfills or use it at a lower level or lower quality structures when we hopefully can use it for high quality structures like highways? And that's food waste oil. We're producing 6 million tons every year that end in landfills. So again, reducing the footprint of landfills and upcycling is really the theme in this study. If you combine all of that with the increased price of oil and the following increased price of asphalt, it makes perfect sense to, join forces with these materials in order to achieve a good quality product. Keep in mind that if you're of asphalt pavement, it costs you about $1 million. The materials itself is about 980,000 of those. So whatever you can contribute towards reusing and even upgrading the properties of the old materials, the amount of savings will be immediately realized. Looked at this step-by-step approach. Again, the focus is the synergy, not whether these materials work or not. So we created this detailed experiment between these additives and the aged asphalt. We already established that it proves aging resistance. So if you columns, this is a unmodified asphalt. This is the level of aging, level of FTIR, the measurement of the formation of carbonyl compounds, which is directly related to the oxidation process. You can see that with all these different types of ashes, we have reduction. The aging. Can you please mute yourselves? Same trend we have seen in the morning, afternoon. The polymer modified asphalt has mixed results, but for the most part, also its aging rate is reduced. So this has been established and published in many papers already by our team. So we moved on using the ash as certain type as I don't know if this is my mic or what is causing this, but as an aging retarding additive. Then the bio oil itself, we started looking at, does it really create a rejuvenating, has a rejuvenating effect or not? So what we did is we compared our developed oil and compared it to market-ready oils. The way you look at the rejuvenating effect is you evaluate the change in the binder before the addition of this additive, and after the addition of this additive, then aging it, then testing. Few these are the different rejuvenators on the get ready through changes in fundamental rheological properties, frequency, crossover modulus, through the improvement in thermal relaxation with the delta TC, through even improvement in the chemistry with the FTIR measurement. And again, that work has been published. So at this step, we know this additive works alone and this additive works alone. Let's take another step further to look at the synergy between them. So they both together can help produce that upcycled product that can also be delivered easily into the system. Ash as a powder to be added to the system will always be competing with the fillers in the system, the fines. So its effect might not be fully realized given the way the industry works. Again, the mixes were not going to be used in the way or created the way we create them in the lab. They are produced in a different manner. So we had to think about this from also the implementation point of view, that the combination of these two additives together provide us with a delivery system that is effective. However, we wanted to make sure that when they are combined together will get us there. So again, we developed a very comprehensive study looking at different wraps, different binders, different properties. Provide at least a proof of concept. Again, synergy. So the first and the most important, in my opinion, test would be looking at the fundamental change in the rheology of the asphalt. I think I saw this graph in two presentations ago for the complex modulus. In a viscoelastic material, you have your elastic component and your viscous component contributing to your overall modulus. What controls the contribution is really the phase angle between them. If you have a change, or if you know at the angle 45, you know that the viscous component, G prime and the G double prime are equal. If this is 45. Through the addition of these additives, a shift in the value of the frequency that leads to this at this degree, or a shift in the value of the modulus at this level indicates a fundamental change in the rheology of the material. And the type of shift indicates if it's an improvement or not. So we looked at the crossover modulus with our additives and the crossover frequency of our additives as a one unit product. Is this rejuvenator and the off-spec ash. Easier by just pointing you to what I want you to see and hide. I don't want you to see. No, there's nothing I'm hiding. If you compare Rejuvenator 1, which is a market sold already on the market in the US, same with Rejuvenator 2, same with Rejuvenator 3. You will notice that the most, for all the combinations of unmodified binder and the OFA, the off-spec ash, and the modified binder and off-spec ash, the gain is typically in the crossover frequency, because that's what rejuvenators do. They soften the binder. That's most of the time, that's what they do. What we have realized that we are having effect on the crossover frequency and the crossover modulus as well. How does that translate to actual performance? So we conducted mixture level testing, as I will show you later. But we also wanted to look at what's the standard state of the, not the standard, what is the state of the art of being applied in asphalt industry right now. Right now, everybody's going after this function because it is a measure of asphalt ductility. It's called the Grover-Rowe parameter. It is measured from the master curve at specific frequency and specific temperature, reference temperature. And it's highly correlated to ductility of the asphalt through other tests and field studies, correlations. So a lot of DOTs are trying to push for using this parameter to replace the typical super pave parameters for fatigue cracking. Now, looking at, with respect to the Grover-Rowe parameter, if we evaluate the binder alone with just the wrap, and when that binder is in the lab to simulate field aging. And we do the same with the rejuvenators and the ash for all the three rejuvenators. So by looking at this column here, this is our binder aged, would be the first row. Second row will be aged with Rejuvenator 1, Rejuvenator 2, and Rejuvenator 3. The higher the value of ability to a fatigue crack. So if you want to compare the purple color, which represents the oil that we generated, as after the application of the fly ash, you will see significant drop in the value of the Grover-Rowe parameters. With the other additives, you see drop in the effect on the binder, but as we incorporate the ashes in them, we're getting some mixed results, or I would say the little bit of increase, no change. So the effect of the ash on the rejuvenators is not as observed or as clearly observed as with this type of oil. The highlight or the circled ones that are the ones that are showing improvement in the Grover-Rowe, and you can see it's consistently with our rejuvenator combined with the ash. But the picture changes significantly as you go to the polymer modification. Again, the dominant component in the polymer modified binder is the polymer, and especially if it's cross-linked like the one we're using. So the incorporation of the particulates sometimes even impede the effect of the polymer. So the improvements we see are scattered all over the place. we don't see significant worsening in the fatigue cracking susceptibility. The performance stays the same, and for the most part, for all the different combinations. So if we calculate the efficiency of these rejuvenators through these formulas, we realize that the combinations that are showing where our food waste oil is used combined with the ashes, even for the polymer modified, we have some improvement and some mixed results. So again, interaction with polymer is complex, and it shows something is hitting here is mixed results. I'm sorry, should have moved down. So after shows, there is a word mixed results missing. So again, like we did before, let's look at the final product and see what the mixture will do with these kinds of materials. But in this case, we are using, for example, the control will be 15% wrap. So there's 15% of the mix already waste material, combined with another 11% from the fly ash and the oil. So we're trying to maximize the amount. And after that, we tried also at 50% and 100% wrap. So 100% wrap means the entire mix is fully waste material. And again, build from there, focusing on damage properties, continuing with the same theme as I talked before. Looking at, this is the semicircular beam test, SCB, where you create a sample with a notch, so you control the crack, and you apply simple bending at a room temperature. What you measure out of it is not only the fracture energy, but the flexibility index, which is the ratio between the fracture energy and the slope of crack propagation. So energy required to initiate the crack, and the crack propagation rate. So the higher that ratio, the more flexible the material. Let's look at this map. Our blue dot here is our binder with 15% wrap. That's the control. It is right at the edge of acceptance. As you add the rejuvenators and even add the rejuvenators with the ash, your value continues to increase. Looking at the fracture energy, the bandwidth is about the same, but what is happening is you're increasing the flexibility through slowing the rate of crack propagation. The green dots represent the ash combination of ash with our rejuvenator. The red dots represent the ash with second rejuvenator. We dropped one of the rejuvenators from the based on the mastic results. So in this phase, we're only doing 2 rejuvenators, the food waste and another one, and dropped the rejuvenator number 1 based on the mastic results. Now let's change the binder to polymer modified binder. In fact, the binder itself, to begin with, would have failed in this test. And so if this was a standard, you wouldn't have accepted this mix to begin with, because its flexibility index is way down here. However, you combine it with this combination of ash and food waste oil, you have pushed it really, really far into the flexible region, which everybody would love to see, only by playing with the binder. Increasing the wrap, again, as I said, aged binder is highly brittle, so prone to cracking. You will notice that the range of performance for the flexibility index is already very low, and most of the mixes are not meeting their results. The only one that is meeting the results, the expect limit, actually, this is not a standard limit, this is recommended by the authors or developers of this test, is the unmodified 15% wrap with the food waste oil. So the presence of the ash in our case here is seems to have dropped the flexibility, but the oil itself has maintained some of that flexibility at 50% wrap. With polymer modified, none of the mixes matched. So it seems that we have been, pushing the limits. With this dosage, again, we had to stick to a dosage and not investigate the dosage at this stage, because that means the study would have mushroomed significantly. And we didn't want to add another variable at this stage. Playing with the 100% wrap, the highest or the most performing mix combinations are the control wrap with the food waste oil and the ones with ash. However, that limit is still not at a very high level. Its flexibility index again has improved to, usually we want some values above 5. So again, 100% wrap, as expected, would be very prone to cracking. And the dosage we have used, yes, have shown a little bit of improvement, but not to the level where you want it to be performing well. But in my opinion, we are actually moving in the right direction. We're increasing flexibility, increasing crack resistance, and that's really the most critical part in using wrap. And what would really, seal the deal for us is working with low temperature. At low temperature, asphalt naturally, even unaged, becomes very brittle. So we did a test on something similar to the previous test. Again, controlled crack, a notch to initiate the crack and evaluate the fracture toughness, fracture energy, and the slope of crack opening. And if you compare at 15%, the recommendations for the fracture toughness is at 800 kPa over a meter squared, and the control for the fracture energy is about 350. All the mixes meet, even the control one without any modification. And that's why really the standards in the US, at least, is to allow up to 15%, because that typically doesn't cause significant deterioration in the performance. Same goes for the polymer modified. But if you increase the wrap content to 100%, you will notice that at low temperature, still meet the requirements. So the recommendations, in my opinion, based on this result, is a little underestimating or what really needs to be met for field performance. But it allows us to do a comparison, comparing our control with rejuvenators, and you will see a drop with Rejuvenator 2, but an increase in the properties with the food waste oil, indicating slightly better performance. Although if you look at the error bars, you'll see some of them are overlapping, which would mean, statistically speaking, there's no change. Even if the average is higher, if the error bars are overlapping, it means from statistics point of view, there is no significant change. But adding the ashes with Rejuvenator 2 at least show a drop in the control, and show little or no change compared to just the Rejuvenator. So the ash doesn't really add any value at 100% wrap. Moving to the food waste oil, you have the similar trend as the control, but also a big drop compared to just the Rejuvenator. So the low temperature is telling us more work needs to be done. However, the idea from different temperature regions seem to be going in the right direction. The game now is about how to create that system better. What is the dosing? Making mixes with 100% wrap is very difficult because of air voids and many other things that are contributing to the fabrication of the mix. But based on the results we have so far, we're looking at, if you're using the food waste oil with unmodified binder or polymer modified binder, you can comfortably reach even above 30% wrap with no significant change in performance. So that's double the current standard by just using these additives and the off-spec ash. In my opinion, the biggest challenge we have faced in this study, I didn't have a chance to go deeper into it, is that the state of practice right now, as we develop mixes because of the effect of volumetrics on the mix design, is not allowing us to have this reach its full capacity. So our next phase with the next PhD student is really to go outside of the box, just drop the specs about how to fabricate samples based on the volumetrics and look for a performance controlled or an engineered mix design, which is everybody's pushing for also right now, to deviate from volumetrics as the basis of mix, which will allow us also to play with the dosing system outside of the norms and see how that. We are dealing with a very different animal right now, different than when we introduced polar modification. So we had to change the way we test, different than when we introduced high traffic volumes and new tire pressures, which led us to develop new tests and new materials. Now we're dealing with a material that we don't have really that much experience in, and further work needs to be done outside. So my conclusion, I believe the combination is effective even as we speak, but up to a certain level of recycled material. And we need to do more work to improve its effect, improve the portions of the recycled materials so that we can achieve further amount and, get into that system of circular economy. So this was a first stage along with another project, just a minute, towards thinking about the structure, the pavement transportation system from a circular economy point of view, of the inputs and the outputs feed into each other. I think this is a nice picture of Temple campus. And thank you and welcome any questions.
Thank you. So we have questions? I have one question. I like very much when you were showing this energy per meter square, all right? The G, because you relate to me, when you show that, it brings the Griffiths criteria for fracture. This is a fracture toughness business, the square root of E, Young modulus, divided by surface energy, multiplied by surface energy. And that, if you read this 1921 paper for Griffiths for fracture, yes, every day, like me, it relates to the interaction energy. So my question was, do you know more about those polymers? Are they charged polymers? What kind of interaction are you dealing with? Because this whole thing, in the end, is all related to this kind of properties, no? I'm always trying to ground things on chemistry, as you can say.
Most of the time, the polymers or the polymer modification is a black box. You're buying a product, you don't control what's in the product. So they sell you mechanical properties.
Okay. But you have no ideas about that, because you have charged polymers, you have tons of different.
We don't see. I'm a rheology person,
okay.
So I look at it from the rheology point of view. I don't know the chemistry and the interface, unfortunately.
Okay.
But the way it's being marketed, it's a cross-linked polymer that will allow for flexibility, recovery, and crack resistance. Extending the range of temperatures for a viscoelastic material. But the chemistry of the interaction, I honestly cannot answer that.
No, just tell you that because everyone knows about cellulose, wood stuff. This is a polymer. But then when we were doing carbon cement with Katerina, then for dispersion, for the reason to disperse carbon in cement in water, we were using this sodium, what's it called?
Oh,
sodium something metacellulose or something. So this is clearly a charged polymer and an ion, and that will be. Say again. Yeah, whatever. Okay, those crazy names. And
I know what you mean. Yes.
You say at the end, you say because one is charged, the other one is not, and it's changed it. Cellulose has nothing much to do with metacellulose, the sodium one. He has, of course, but in terms of interaction, totally different.
The way we include the polymers in the asphalt is more of a forced dispersion using high shear mixers.
Okay.
Over a very long time.
Okay.
So even from my little understanding of dispersing agents, that is their effectiveness lasts a short time.
Okay.
So the modification, the way they do the modification, it takes a few hours of high shear blending.
So a few hours means a lot of interaction.
Yes, to activate the interaction and
Yeah.
to infuse or integrate
Okay.
the SBS or whatever polymer you're using into the molecular structure of the asphalt.
Okay.
That's again the extent of my
So
knowledge.
maybe it will be kind of a way to kind of optimize the thing with those properties. Like if you know in advance that type of interaction you may expect that also relate to how strong they are, then
That's
you
why
can
these
make
people hire a lot of chemists and
yeah.
never engineers.
Yeah,
to be
of
honest.
course. Yeah. Okay, sure. I was talking actually at some point we were discussing with W.R. Grace, and they are the chemists of cement, and they play around with those super plasticizers and things. It's a whole.
And they come to conference and make fun of all the engineers who have been doing a lot of tests.
Rightly so. I mean, I'm fine. Sorry, it's a joke. Any other comment, questions? Constantine, you're quiet. What's wrong with you? Are you okay? Are you sick?
Long day. It's a long day.
Are you okay? Yeah.
Don't tempt him, please.
No. I like to add again, I think asphalt is maybe last polymer which we produce without incorporation, like fillers, controlled design incorporation of the fillers. And this is what we are trying to address. And using very low quality waste filler material, we achieved this beneficial interactions which were not there when we would use like a classical backhouse filter which is collected. So fly ash obviously has in off-spec fly ash has a great potential to be combined with asphalt material. This is where we are. We can look on maybe high-end.
On the chemistry of the fly ash against the asphalt and what elemental analysis and the components and do a statistical regression models between the elemental components of the fly ash and its physical and chemical components with the performance. And you touched on one of them. Silica was up there.
Yeah.
Obviously, particle size distribution indicators.
Sure. Yeah, but
I was saying really up in the, and I can't remember. I think sulfur content.
You know, this what I was saying this morning about the silica thing is because the placement it was 145 degrees. So there are many ways to charge inorganic materials. Either you put it in pH, low pH you heat OH group, and you put water. High pH you heat H groups and still put water. So you have O minus left. So you change the sign. But one way to do that is also with temperature. You can break OH groups with temperature. When you have this silica at 145 degrees as this morning, you're having charged silica thing that are prone to react, basically. You're activating it. This is the title of your talk this morning was reactive, right? So here is kind of the same somehow because of the polymer, they might have some interaction because they are some are charged, some are uncharged. So yeah, we react more or less with the asphalt and the fly ash for the same reason.
Can I ask you how to test for that?
I tell you the amount of OH group per nanometer square. So it's not easy for take C2S, C3S. You know, these are crystals. All right. So you can take a different cut for the surface and imagine what will be the 111 surface of the 100 surface. And then you count how many O groups are the surface. In real life, those groups will be not just dangling O's, they will have an H attached to it. And you know the surface area, so you divide this number by surface area.
And it's very difficult to cut.
No, I'm saying this is on the computer from crystallographic thing.
Oh, okay.
All right. So that's the idea. And then, for instance, I think the reactive clinker is the gamma C2S, isn't it? You know that there are different.
Would a calorimeter work?
Yeah.
A calorimeter work for us?
Yes. Oh, you can do a TGA analysis. When you see that, yes. You know, you will dissolve the physically bond water up to 60 degrees, and everything that's coming as water after that is broken OH groups. So that's the way to quantify this.
But we don't have the hydrated product. So
no, I'm talking about the dry thing. The thing. When I say the water, you may have some water absorb the surface a little bit, fine, but that will go away at 60 degrees.
Oh, yeah.
I'm saying breaking off the surface group, and that's a way to evaluate how much you have of OH groups per nanometer square.
I think Ahmed might be interesting idea. We try to explore in one of projects to measure contact angle actually on
But
the
that
compressed
waterability is actually, yes, it's related to that.
on compressed
yes.
powders. So we can make a powder compacts and just put a droplet of
Very good.
binder and modified binder, and we can check the contact
So
angle.
excellent.
From
That's-
contact angle, you
That's
can
very good because
But-
actually
but,
a silica surface will go from hydrophobic to hydrophilic at a frontier about 5-6 OH groups per nanometer square. So below that, you hydrophobic, below that, you go to hydrophilic up to this limit of 11, I think it was, for whatever silica, and that is super hydrophilic.
But wouldn't particulates like fly ash suspended in the system
But
influence the
flashes are
result?
silica things, right?
alumosilicate.
Aluminum silica, okay,
Yeah.
silica
Plus,
base.
some of those products were doped with like high quantities of lime because lime was injected into the system and
Okay.
remained there,
Okay.
maybe partially carbonated.
Okay, so I mean, but I think your idea of measuring the contact angle is
I
good.
even-
Good thing. So you should shoot for the most hydrophilic, which means the one that makes the water to spread at the
It
surface.
was actually a cool concept back in 90s, I believe, this powder and contact angle polymer interaction with the filler.
Yeah.
And actually, one of our colleagues, he won even NSF one CHRP project. Ahmed, you know the guy. And but one paper which I tried to examine the active groups in the fillers. We were trying to publish it a few times and it was rejected a couple of times for different reasons.
Okay.
And it's actually somewhere sitting in the, in unpublished, but Ahmed, maybe I share with you. And
Let's
maybe
do
you can look at it and maybe we run an experiment
yeah,
and we have more idea about interaction.
So yeah, so the most reactive one will be the most hydrophilic ones.
And maybe we publish it somewhere in the conference so we can still reference it, maybe.
Yes.
Right.
All right.
Good discussion.
Yes, thank you for discussion.